Okay. So, all right. So what I mean at the infinitesimal level is, I have this picture, this parametrized surface. I just take a small portion of it close to s equal to 0, right? So close to gamma naught, infinitesimally. Then what should be the infinitesimal object? If I look at s infinitesimally close to 0, what remains of this picture? Just this vector field j, right? Yes, that's what you see at the infinitesimal level is you just see j, right? When s is infinitely close to 0, you just see j, right?
Yes.
So you think of j as giving you an infinitesimal strip, an infinitesimal parametrized surface where s is infinitesimally close to 0, right? Okay, so that is what j is. It's giving you an infinitesimally close thin strip. It's giving you an infinitesimally thin strip such that, you know, basically here, let me draw you the picture. You have j at the infinitesimal level. What do we have? We have j, a Jacobi field. So our parametrized surface such that all the gamma s's are geodesics gets replaced by a Jacobi field, in the sense that here's my gamma, and then I have this j along it. Okay. And j is an infinitesimal analog of this parametrized surface, in the sense that if I move along j infinitesimally, then I will get a curve which is infinitely close to gamma, which is also a geodesic. All right. So it's an infinitesimal variation of a geodesic to another geodesic. Okay, that's the idea. So at the infinitesimal level on the left-hand side, we get Jacobi fields replacing these parametrized surfaces such that all the gamma s's are geodesics. Okay. So this should be in one-to-one correspondence with what we have at the infinitesimal level on the right-hand side. So on the right-hand side, we have a curve in Tm, right? So what should the infinitesimal object corresponding to this curve be? It should be its derivative at time 0. Yes, that's the infinitesimal object. Yes?
Yes, sir.
Derivative of what, sir? The curve, right? The speed of the curve.
The curve in Tm, right? The derivative of
Yes,
this.
yes, yes.
Xi equal to z prime 0 in t theta Tm. Okay. J equal to here del f del s at s equal to 0. Right. So we should have a correspondence between Jacobi fields on the one hand, a one-to-one correspondence between Jacobi fields and tangent vectors to the tangent bundle, right? The vector space T theta Tm, right? And at the infinitesimal level, these correspondences should be linear. So in fact, what should we have? We should have an isomorphism between the vector space J gamma and the vector space T theta Tn, right? Okay. Does it make sense?
Yes, sir.
Okay. So let's make this more precise. let's make this more precise in the following proposition. So uh, let theta be a point PV in Tm. Okay. And let gamma of T be the geodesic with initial condition PV. So it's XP of TV. Okay. This is a geodesic. So let xi be any element of T theta Tm. And let so S in say minus epsilon epsilon maps to ZS equal to alpha S. Sorry. Oh, sorry. No, sorry. What am I doing now? It's correct. Yeah. So let xi in T theta Tm and let S in minus epsilon epsilon maps to Zs equal to alpha S capital Zs in Tm be any curve such that Z prime 0 is equal to xi. Okay. So I'm taking a tangent vector to Tm at theta, and then I'm taking a curve passing through. So Z0 is, so maybe I should write it the other way. So Z0 is theta and Z prime 0 is xi. Okay. Then, so this curve is going to give me a parametrized surface. That parametrized surface is going to give me a Jacobi field, right? So let f of st equal to x sub alpha s of t zs, right? Okay. And let j of t be the Jacobi field del del s at s equal to 0 of f of st. Then j is the unique Jacobi field along gamma So which will depend only on xi. Okay, let me just write it such that J0 equal to d pi theta of xi, the horizontal component of xi, and J prime 0 is equal to k theta of xi, the vertical component of xi. So we denote J by J is equal to J sub xi, right? Because this only depends on xi. Okay.
So we're also saying that my Jacobi field might come from different parameterized surfaces. Right?
Right.
It's not
But
dependent on the parameterized surface.
no, it only depends on the tangent vector xi here.
Mm.
Okay. So basically, the Jacobi, the parameterized surface corresponds to a curve, right? But the Jacobi field which you get by differentiating the parameterized surface with respect to S, that only depends on the derivative of this curve in t theta tn. Right? That's what it's saying. The Jacobi field only depends on the derivative because the Jacobi field is determined by its initial conditions J0 and J prime 0, and those are determined just by xi, right?
Exactly.
So and xi is just the derivative of the curve Zs. So it only depends on Zs up to its derivative. All right. Okay.
Yes. Okay.
So the proof is just a simple computation. I mean, but maybe you'll see it better if I draw you the picture. So here's the picture. The picture is you have this curve in the tangent bundle, right? So that means you have a curve alpha and you have a vector field Z along alpha, right? So here you have Z0 is equal to V and alpha 0 is equal to P, right? And then I'm looking over here, I have some alpha S and I have some ZS, right? And these give me geodesics, right? So this is my gamma and this is my gamma S. So gamma is equal to gamma 0, right? This is the picture. Is this clear? Yes?
Yes, sir.
So what is J0? J0 means I fix t equal to 0 and I differentiate in the S direction, right? So that will be just the derivative of this curve alpha, right? At time 0, right? Yes?
Yes, sir. Yes.
Right? So what is J0? J0 is del del S at S equal to 0 of gamma S of 0. So this is del del S at S equal to 0 of alpha S, right? Now what is alpha S? It is, so this thing, this pair is equal to my little Zs, right? So alpha S is pi of Zs, right? So this is del del S at S equal to 0, right? This is the foot of the element Zs in Tn, right? Of pi of Zs, right? So this is by the chain rule d pi theta of DDS at S equal to 0 of Zs which is d pi theta xi. Is this okay?
Yes.
Okay. Now what about j prime 0? All right. So here we have to be a bit careful. So here there's a little picture also, but this is a bit harder to understand. So you think of S infinitely close to 0, okay? So J is basically the arrow joining these two dots. Okay, this is J0. All right, think of this as J0. Okay, and now what is J of T when T is small? That's going to be the arrow joining these two dots. Okay, right? I move along a small distance T and then I join the dots here. Okay, yes? So what is J prime T? J prime T will be, I have to look at how the head of this arrow changes from this arrow, right? So that means I have to move this arrow up here basically. So I sort of move it like this. Okay. And this little difference here will be J prime 0, right? Okay. But that is the same if you look at this picture as moving this arrow over here and looking at the difference in this between these two heads here. So that difference is how the head of this ZS moves, right? So that will be Z prime 0, right? And what is, Z prime 0, the covariant derivative of Z, that by definition is k theta of xi, right? Okay. So that's the intuition, that's the picture. You try to understand this picture, okay? But the calculation is a simple one. So what is J prime 0? So this is dd, so d del t at t equal to 0 of J of t. So what is J of t? J of t is del s at s equal to 0 of f of st, right? Yes, this is by definition J prime 0. Okay, yes.
Yes, sir. Yes.
Okay, now we can use what can we use now? I have d del t of del s. So what should this be?
These two commute that thing.
Right, I can use symmetry of the parametrized surface, right? So this will be the same as d del s at s equal to 0 of del t at t equal to 0 of, so f of st is just gamma s of t. So the derivative of this with respect to t is just this zs, right? At time t equal to 0, gamma s prime 0 is zs exactly. So this will become what I was saying. This becomes just d del s at s equal to 0 of zs, right? And this, by definition, this is exactly the definition of the connection map, right? This is exactly k theta xi. Is this clear?
Yes, sir. Yes.
Okay. So this is the computation, and the picture is this little quadrilateral, like this trapezium here. Try and understand this picture a bit, okay?
That
You
gap
have-
between those two heads, that is your J prime 0. That's what you said, right?
Yeah, this gap between these two heads, you can either think of it as moving this vector up here and looking at how this head changes, that is J prime 0, or you can also think of moving this vector here and looking how this head moves.
Actually,
is-
sir, when you're saying that moving this vector here, we actually can't see which vector. Can you use a different ink, then it will be clear when you're saying, just put a mark on the thing.
this vector, this vertical vector. You can see the cursor. You can see the cursor, right? Yeah, the cursor. You can see the cursor. So moving
No.
this
No,
vertical
sir, actually, it's
horizontal.
blinking.
Cursor is not.
Oh, I see.
Yeah,
Oh, you can't see the cursor.
no.
Oh, okay. So, acha. What's a good color? Blue. So, right. So this vector here, moving this here, right? Or that's the same as, let me use, say, red. This red vector here, moving this here. Okay.
Okay, so now it's clear.
And this difference is the, I mean, I can look at it as the difference of going from here to here, or from bottom to top, or from right to left, So that is this equality, J prime equal to K theta of psi. Okay. Does it make sense?
Yes, sir, it's okay.
I mean, this is just the intuition, right? So just to give you intuition for infinitesimal pictures. I mean, these are infinitesimal pictures, okay? They're not global or local pictures. They're infinitesimal pictures. So, I mean, maybe you're not used to thinking about them, but I like to think about them. So I'm just sharing them with you. Okay. So, all right.
Yes, sir.
I mean, calculus is basically infinitesimal stuff, right? It's just looking at small changes, infinitely small changes. That's all calculus is. So this is just calculus. It's nothing else. It's just calculus. It's infinitely small changes. Okay, so let me go back to black now. Where is black? This is black. Yes. Okay. So, so as a corollary, what do we get? We get that the map psi from t theta tn to j gamma xi maps to j xi. I mean, this is not really a corollary. I mean, so let me not call it a corollary. I'll just state this. So observe. The map xi maps to j xi is an isomorphism. Right? I mean, in fact, what is the actually what do we have? We have basically, so in fact, we have here t theta tn. So this is mapping by the map little j theta equal to d pi theta k theta. This maps to TPM direct sum TPM, right? And then we also have J gamma, which is the map of initial conditions phi, right? J goes to J prime 0, J0, J prime 0, right? And this map is just the map which makes this diagram commute, right? So in fact, the following diagram commutes, right? Is this clear? Yes?
Yes.
Okay. Is it clear to everyone? This diagram commutes?
Yes, sir. Yes.
I mean, this is how J xi is defined, right? J xi is defined to be the Jacobi field whose initial conditions are d pi theta of xi, k theta of xi. That's exactly saying that, you know, this psi is, I mean, this diagram commutes, right? It's exactly saying this. Okay. So these two maps are isomorphisms. This J theta we already saw is an isomorphism, and this phi we showed above is an isomorphism. So obviously this this diagram commutes. So this arrow is also an isomorphism, right? Okay. So that's why Jacobi fields are important in another sense now, because the we can think of the space of Jacobi fields as the tangent space to the tangent bundle, right? Does it make sense?
Yes, sir.
Okay, and this is the picture, right? The picture is this picture here, that you know, your tangent space to the tangent bundle t theta tm, that means infinitesimal changes in this vector v, right? So infinitesimally moving this arrow from here to here, but that arrow determines for you a geodesic, and if I move this geodesic infinitesimally, then I will get a vector field along this geodesic, right? Which connects this geodesic to this infinitesimally close geodesic, right? I get these arrows which join these two geodesics. Okay. And basically what happens is, if I have two infinitely close geodesics and I join them by arrows, then those arrows have to satisfy a second order linear differential equation, which is the Jacobi equation. Okay, those arrows have to be a Jacobi field. Does it make sense?
Yes, sir.
Yes.
Okay. Okay. And now, once we have this, we can also talk about the derivative of the geodesic flow in terms of Jacobi fields. So we can write the derivative of the geodesic flow in terms of Jacobi fields. So let say phi t from Tm to Tm is the geodesic flow. Okay. And I take theta equal to PV in Tm. And I take, as usual, gamma to be the geodesic with initial conditions theta. So gamma t is xp of TV geodesic. And then how should I write this? So then we have the following. So see, my derivative of my geodesic flow phi t maps theta to phi t of theta. So its differential will map the tangent space t theta tm to so d phi t will map t theta tm to t phi t theta tm. So note, what is phi t of theta? Phi t of theta is gamma t gamma prime t, right? Yes, by definition of the geodesic flow. Okay. Yes, theta is gamma. I mean, theta is gamma 0, gamma prime 0, right? Yes.
Yes, sir. Yes.
So now I have my isomorphisms here. I have my j sub theta. So that will map to TPM, direct sum TPM. Okay. So a xi here. So writing this will be a bit awkward. And I have j sub phi t of theta here. So this will go to t sub gamma t m, direct sum t sub gamma t m. And okay. So what should I call this map? It's not parallel transport. It's what is this map? I don't want to use J because I've already used J. So what should I call it? Okay, let me just call it QT. Okay, fine. I can't think of a good word for it. QT. Okay. Where so the following diagram commutes. Where QT is the following map. It maps, so I take a pair of vectors in TPM, v comma w. So these I can write as uniquely for some unique Jacobi field as J0, J prime 0, right?
Yes, yes, we can do that.
And then I can look at this Jacobi field at time t, and I look at its conditions at time t. So this maps to Jt, J prime t. Okay. So let me remove this we have in the following diagram commutes. So this J here, so given J is the unique Jacobi field. With initial conditions VW. Okay. So it's just the map J0, J prime 0 maps to JT, J prime T. Okay, so this is the differential of the geodesic flow. After you identify T theta Tm and T phi T theta Tm with the tangent space of M plus tangent space of M via the usual maps, right? Okay.
Yes, sir.
Is the statement clear?
Yes, yes. Statement.
So this QT is a linear map, right? Because this J depends linearly on VW. This is just the inverse of the isomorphism we gave, right? Phi from the space of Jacobi fields to the TPM direct sum TPM. It's the inverse of that map, then composed with the map J goes to JT, J prime T.
Yes.
Right?
Right.
So this is a linear map. This is a linear map. Okay, this is an isomorphism because it's a composition of two isomorphisms. So. And I mean, you can also see it's an isomorphism here because these J theta, J phi T theta, these are isomorphisms, and well, phi T is a diffeomorphism, so D phi T is an isomorphism. So all of these maps are isomorphisms. So, I mean, the proof is just a calculation. So you let Xi, I mean, really the proof is just a picture. It's not even a calculation. It's really just a picture. If I draw you the picture, you'll see. So let Xi be an element of T theta Tm.